All right, so let's do the last little bit of fill-in notes here. We got the Chernobyl power plant. You should know that Chernobyl was one of the two meltdowns. The other one was Fukushima, Japan. This was the world's worst nuclear accident. Firefighters were the first responders. Then they were taken to the hospital to die, which you saw when you were watching the video there. The half-life of cesium-137 is about 30 years. That's how long it takes for half of the sample to decay. Then we need another 30 years to pass before half of that, before we get down to a quarter of the original sample. And then another 30 years for another half of that to go down. So it's going to take a very long time. People aren't going to be back in Chernobyl living there for hundreds of years. They actually just finished building a concrete sarcophagus to enclose everything, because some of those isotopes, especially U-238, they're not going anywhere. So they have a half-life of 4.5 billion years for half of them to decay. So when the Earth's lifespan is over, only half of the U-238 would have decayed away. You got to wait another 4.5 billion years for the other half to decay. I don't think anybody's waiting around that long. All right, what is a bonus of this half-life business? How can we use this in the real world? Well, we can use it. Here's an application. We can use it to date things, to find out how old things are. People aren't just guessing at how old things are. People actually know, because in the air, there's carbon, and you guys are familiar with carbon dioxide, but there's carbon that is typically C12. This is a normal, boring, stable carbon. We've got 6 protons and 6 neutrons, and this is very, very abundant. 99% of the carbon in the air is carbon 12, but there's a trace amount of carbon 14. This doesn't have that nice 1-to-1 ratio. We got 6 protons, 8 neutrons. Not 1-to-1. It's unhappy. It wants to undergo beta decay, and it wants to end up, well, it's going to end up whether it wants to or not, but it wants to end up stable. So it's going to shoot out a little electron when the neutron flips and becomes a proton. That turns it into nitrogen. It's no longer carbon. So you see a decay curve. The amount of carbon-14 goes down, down, down in a predictable manner. And the half-life is crazy long. We use carbon-14 because it decays. Carbon-12 is stable. That's useless. That's the green one. That doesn't decay. That doesn't help us. But the carbon-14 goes down, down, down in a predictable way. And we can use that curve to help us figure out how old things are. So now let's think about this image here. We've got carbon coming out of the atmosphere going into the plant. That is photosynthesizing. Little cow over here can't photosynthesize, but the cow can eat the plant. So if the plant gets carbon-14 from photosynthesis into its plant matter, and the little organism comes along and eats that, or maybe you are eating some sort of vegetation, you get that carbon-14 in your body. Or maybe you eat the cow that ate the vegetation, so you get the carbon-14 again in your body. As long as the plant is living, it's photosynthesizing and getting carbon-14, which is always going to be replacing the carbon that's decaying. As long as the cow eats, it replaces the carbon-14 that's decaying in its body. As long as you eat, you're replacing the carbon-14 that's decaying in your body. The problem comes in when the organisms die. Because this decay happens, the carbon-14 drops and drops and drops, and nothing gets replaced. Because when it's dead, it can't photosynthesize or eat. So let's go through some of these notes here, and then we'll see how we use this information. So both C14 and C12 are absorbed by plants in the same ratio as present in the atmosphere. You have to know that carbon-14 is very rare. Carbon-12, the nice stable carbon, is most abundant. They're both taken in by animals as they consume the plants that once took them in. That carbon-14 is decaying, but since the living organism is constantly taking in new carbon-14, the plant is still photosynthesizing, taking more out of the air. Animals are eating when they're alive. You are included. So you're constantly taking in new carbon-14. So the level of C14 pretty much remains constant. Yes, some decays, but it's getting replaced. That's true while the organism is alive, because it's eating and replacing the C14. But when you die, you're not taking in any more carbon. That changes the ballgame here. So the only thing that can happen is that carbon-14 is going to decay at a very predictable rate. It's an exponential curve. It's going to decay into nitrogen-14 at a regular rate. The half-life is 5,730 years. You should also know that carbon-12, this is boring. This is like the brick in the fire. It's not a crazy unstable dragon. It's not going to change because it's stable. So if we have something that is stable, never changing, and we have something that's changing, we could look at the ratio between them. So scientists will measure the amount of C14 left and compare it to the amount of C12 that's in that organism, and they can find out how old an organism is once they compare it to the graph. So let's do an example of this. Here's the percent. Remember, it's going to be based on a starting point of 100%. But here's our carbon-14 that's remaining as time goes by. So at time 0, before the organism has died, it's got all the carbon-14 it's going to have. Then we push start on the stopwatch. Time starts ticking. And that carbon-14, this curve is carbon-14, it starts going down, down, down at a predictable rate. So we know if we start with 100% after the first half-life, we're going to have 50. So if you go over here and you look down, that's what the half-life of carbon-14 is, 5,730 years. That's not really what we're asked to do with this problem, but that's something by now you should understand. Let's now read the problem here, and let's use this graph to answer the problem. It says 2 bones were found about 100 meters apart from one another in an archaeological dig site. Bone number 1 has 30% of the C14 that living bones contain. So let's make a little note over here. Bone 1 has 30% of what it should have had when it was living. Should have had 100% when it was alive, but it's not alive anymore, so it only has 30%. Bone 2 has 80% of the C14. What are the approximate ages of these bones, and could they both be from the same organism? So this is how much C14, the percent of C14 that they have compared to how much they had when they were alive, which should have been 100%. So let's look at 30%. If we start at 100, go down, 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 down to 30. Then we go over till we hit the curve. We hit it right there. We look down, and that tells us it's been dead for about 10,000 years. So 30% is about 10,000 years old. 10,000 years have passed since you hit that starting button on the stopwatch, since time 0. Now, the other one has been dead for a different amount of time. How do we know that? Because it has a different percent. It has 80% of what it used to have. It used to have 100. This has 80%. So it hasn't been dead for that long, and we know this because it's still got a lot of the C14. It hasn't had time to decay. So you go over to the graph, and then you go down, 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 and it's kind of in the middle somewhere there, between 0 and 5,000, so we'll go with 2,500. So we now know that these two organisms can't be from this, or these 2 bones can't be from the same organism. They have different amounts of carbon-14 compared to what they should have had when they were alive. And if we look at the curve and use the curve, we can figure out how old they are. If a sample is older than 50,000 years, remember we talked about how that makes things kind of tough. There's a lot of uncertainty when you're trying to measure very, very small changes at this end of the graph. So when things get a little difficult and hard to differentiate, and there's a lot of room for error, then it's not that the science is wrong, it's just that we need to use a different isotope. We can't use carbon-14 if things start to get around 50,000 or older. So instead, we're going to be using another isotope. And there's crazy amounts of isotopes out there that can be used for all different things. And I think that's it.